we shall start our last part of our afternoon session. Before start, I would like to remind the participants that the onlookers cannot talk to our participants. Okay, so you can say, you can hear what they talk about, you can say anything to them. Alright? Okay. Now, the opponent, please propose the problem for the reporter. You have 1 minute to consider.
Problem 4, ion magnets.
Problem number 4. You have 1 minute to consider.
We accept the challenge.
Okay, problem number 4 will be for next problem to discuss. Alright? 7 minutes for the reporter to prepare. Please write down names from each team to take part in this problem. Because you told us please take the floor. You have 12 minutes to present your work.
Honorable juries and fellow competitors, I am the reporter from Team Excelsior, and for today, we'll be reporting problem number 4, climbing magnets. The problem statement reads, attach a rod assembled from cylindrical neodymium magnets horizontally to a vertical ferromagnetic rod. Limit the motion of the magnets to the vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. For today, we'll be mainly focusing on 1. What forces or causes make the magnets climb upward? And 2. How do relevant parameters affect the climbing speed? This is the outline of our report. First, we'll talk about our preliminary experiments, and we'll talk about the phenomenon explanation. And we'll give a force analysis for this phenomenon. And we also talk about the verification when it's not climbing. Next is our theory. We'll first talk about some definitions for some variables. Then we'll talk about finding a point called ICOR, the instantaneous center of rotation. Then we'll mention some boundary conditions for the magnets to move upward. Next, for experiment, varying the angular velocity, mass, and distance between the rod and ruler will be discussed. And finally, we'll have our conclusion. First is our preliminary experiments. So this is our setup. As we can see, a ferromagnetic rod is fixed at the center of the table when, with a variable speed motor conducted at the base and right in the middle of the table. We also have, we attach some neodymium magnets to the side of the ferromagnetic rod. Then we have a stabilized ruler on the side. So because as the problem statement says, we have to limit the magnet's direction to a vertical direction. So we have a stabilized ruler, so it will limit the horizontal motion of the magnet. Here is our observation video. As we can see, when we turn on the variable speed motor, we can see that the magnets will move upward and along with the ruler. And this was the 3D motion and 3D simulation for our experiments. Next, we'll talk about, if we look closely, we can see why the magnets climb up. So here is a slow motion video. As we can see, the magnets will first pivot to the left-hand side and roll up and then slip again. This is called the stick-slip phenomenon. And as we can see from the slow motion, it will slip to the left-hand side first, and then it will roll back again. So we'll first talk about, we're assuming that this is the bottom of the magnet, and when it's not moving, it will have contact points forming down straight down the middle. So we first separate the stick-slip phenomenon into 4 phases. The first phase is when the contact points are aligned down the center. And first is when the contact points are aligned down the center. And it was shown in the previous picture. This is the phase where neither the magnets or the rod is moving. Next is when the rod spins, the kinetic friction will cause the magnets to slip to the left-hand side. And because the magnets slip to the left-hand side, the contact points will move to the right side. Then, we can see that the normal force in the lower part is relatively higher compared to the upper part. So the difference in the normal force would actually cause the magnets to start spinning. Then, pure rolling happens. Pure rolling happens at the pivot of the point, which is the instantaneous center of rotation. And it will happen at the lowest contact point as a pivot. With all that being said, these 4 motions would repeatedly happen to ensure a steady speed for the magnets to climb up. So it will happen again and again for it to climb up. Next, let's talk about finally, let's get a force analysis for this experiment. So first of all, there is a static friction that holds the magnets to ensure that the magnets won't fall down. Then we can see that the magnitude of the normal force is equivalent to the magnetic force at the horizontal component. And because we also have the torque equilibrium as well, so we can see that when Newton is times omega, it will be equivalent to the static friction divided by 2. So in this stance, both the static equilibrium and torque equilibrium happens. So we would first like to clarify also why the lower part receives bigger normal force. Because as we can see in this force analysis here, the normal force is pointing downwards and it is closer to the lower contact points of the magnets. And as previously mentioned, this is why we said that the normal force at the lower contact point is actually higher than the upper contact point. And we also like to clarify, why is it pure rolling instead of just kinetic friction? Well, because friction is opposing to the direction of the relative displacement. So because the magnets move upward, then theoretically the friction should point downward. However, the net force of the magnets should point upward. So these two statements are contradictory to each other. So this is why we can prove that it's pure rolling that makes the magnets go up rather than kinetic friction. And of course, we can have some clear verifications when it's not climbing. As we can see, when we have the roller really close to the ferromagnetic rod, it will not climb, and even it will maybe start to fall down. This is because there's not enough space for it to have the stick-slip phenomenon. There's not enough space for it to slide. And also, when there's no normal force between the contact points, when the magnets are facing downwards, even if we spin the ferromagnetic rod at high speed, it will not climb up. So these are the proof. Next is our theoretical model. We'll first like to define some variables. So consider one of the contact points P. And the velocity of P could be shown as the equation over here. And we can divide it into two components, the spinning component and the vertical climbing component. And we can also assume that the contact point P, there's an instantaneous center of rotation in one of the contact points. And the instantaneous center of rotation would have to fulfill these two equations that we listed. And if we can obtain through experiments, we can obtain the radius and the capital omega, lowercase omega, and the velocity of our experiments. So if we can calculate the L and theta of our experiment, we can ensure that it's actually, there is actually an ICR that exists. So through experimental data, we can find out that that ICR really does exist. And it's actually at the contact point P over here. And because we also found that because L roughly equals the radius of the magnet, so we can see that it's, the contact point is, the ICR is almost at the lowest contact point of the contact line. And we can also find out that different angular velocity doesn't affect the cyclic distance, which means that the theta remains a constant for this situation. So we can say that the velocity of the magnet is proportional to the angular velocity. And here's the boundary condition. So when the magnets climb up, there will be we'll have two static frictions at the vertical and horizontal component. And there will be a kinetic friction for the ruler. And we could also find out that there's a torque that's defined as clockwise and counterclockwise. And if we subtract these two torques, then it would have to be larger than 0, so that the climbing rate is also larger than 0. So when we have a small conclusion, when theta degree increases, or the kinetic friction of the ruler, or the radius, or the force to the static friction to the vertical direction decreases, magnets climb up easier due to the larger torque. Here's our experience. We can find out that clearly when we have a larger angular velocity, the climbing rate will happen higher. However, you might find out that when there's unsuccessful climbing, we find out that the boundary limit is at 65 radians. So when it's before 65 radians, it will not have not be climbing steadily, or you have some deviations. But afterwards, it will have a straight line that fits our theory line. And this is because that the static friction is not enough to make the magnets move upward. Next, we verify. Next is varying the mass. When we vary the mass of the magnets increase, so the side-slip distance decreases because it has a bigger inertia. So it's harder for the magnets to climb upward. So that means that theta angle increases, so climbing speed V decreases. And this is varying the distance between the rod and ruler. So we find out that with the greater distance, it enables the magnets to side-slip more on the contact surface, which resulting in a smaller theta. And resulting in a smaller theta would mean the magnets climb upward faster. This is our conclusion. Our first question is, why do the magnets climb up? So first, we define the Stickson phenomenon into 4 phases, and as we previously mentioned. And there are some influencing factors as well. We had the verifications for when the magnets will not climb up. When there's no normal force difference, then the magnets will not climb up. And when there's not enough space for the magnets to slip, it would not occur the Stickson phenomenon. So it will not climb out. So it will not climb up also. And how do relevant parameters affect the climbing speed? We can find out in this chart that it will start from a stable climbing to a steady climbing, which in case the velocity is proportional to the angular velocity. And the decreasing of the mass will cause the side slip to increase, meaning the velocity will go up. And increasing the distance between rod and ruler will cause the side slip to increase, so the velocity will also go up.
Okay.
Thank you for listening.
Okay. The opponent has 2 minutes to pose questions.
How do you measure the spinning of the velocity?
We analyzed it using tracker because we analyzed a point where it spins. Wait, did you say angular velocity?
No, that's the spin.
The spinning of the magnet. So we use tracker to analyze so how many times it spins, and then we would convert it into radians.
So that is related to the radius of the magnet.
Yes, it's actually lowercase omega, like we previously mentioned in our report.
And how about without the ruler? What's the difference between the movement of the magnet?
So according to a problem statement, they want us to limit the magnet to the vertical direction. However, because there is a Stickson phenomenon occurring, so if there's no ruler, then the magnets will actually spin and climb up simultaneously. But that's not what the problem statement asks, so we add a ruler. So if there's no ruler, then we'll spin and climb up.
Well, check the material of the rod. How will this affect the experience?
The report didn't conduct experiments for using different materials of rod because we believe that it would fulfill, because we use we use an iron ferromagnetic rod because it fulfills the promised image requirements, and because also the other ferromagnetic rods are very expensive and very uncommon. But however, it would change the magnetic strength between the magnets. So we didn't conduct experiments, and that's what it will change. The magnetic strength between the rod and the magnet.
And will the name of the magnet influence the velocity of the
Volume?
volume?
Okay, time is up. 3 minutes preparation time for the opponent. 你可以有可能还是 maximum 4 minutes to discuss these viewpoints. Followed by a discussion between him and the reporter for a total of 14 minutes.
Okay, I'm the opponent from the team cell. Common statements. The touch rod assembled from cylindrical neodymium magnet horizontally to a vertical ferromagnetic rod limits the motion of the magnet to the vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. About the experiment setup, they use the variable speed model as a parameter, and also they use the stabilized rule to control the parameters of this experiment. About the theory, mention and also calculate the ICOR, and also they consider about the condition, the boundary condition, and give the clear explanation of the experiment definition. And the point of the theory, in my opinion, is about slip and sinking to climb up. The magnet will slip and sling to the rod and climb up. The main idea of the experiment is the space for slide to climb up, and also the slip and slinking to make the magnet climb up. And also they mention the larger torque make the magnet climb easier. And when the mass decreases, velocity of climbing magnet increase. About the pros and cons, about the pros, speak an explanation about how the climbing magnet climbing very clearly and easily to understand. And they also consider about many variable issues. And in the end, they're related to the statement and did a well job. And about the cons, I think that some chart could explain more clear for the audience to more easier to understand. Okay, this is for all. First question, will the touch area between magnet and the rod affect the experiment?
The contact area between the magnet and the rod.
Touch area.
What do you mean affect? So do you mean like if there's a
Like velocity or the speed, the velocity of magnet speed?
do you mean if we change the contact area of the magnet? Well, if we change the contact area of the magnet, that would mean that we would use like probably maybe a bigger magnet for the contact area. However, it would if there is still the same if it's still the same mass, if it's still the same volume and all, then theoretically it won't cause too many changes. However, it will cause the slipping distance to be shorter. So it will probably cause the magnets to have the whole climbing motion move slower.
So if the other issue is the same, then it won't cause any.
No. I'm saying that if the contact area is bigger, then supposedly it would cause the stage phenomenon to have a shorter distance. So it would cause the whole process to move slower. So it would cause the whole magnet to climb slower. Yes.
power of the magnet spin to the rod will influence the velocity.
Can the reporter say it again?
The power of the magnet talk to the rod.
Okay. So, are you saying that if the magnet's strength is stronger, how will it affect the experiment? Well, then theoretically it would cause the magnets to climb also slower because it has a stronger normal force towards the ferromagnetic rod. So it would theoretically make the magnets climb slower.
Is that a simulation or really done it?
No. So, is the reporter considering if we added multiple magnets to the experiment? Like if we change the magnetic strength, we have to add multiple magnets, right? So the reason we did not conduct the experiment is because if we add multiple magnets, it will actually vary two parameters at the same time. It will vary the mass and the magnetic strength. So we didn't conduct the experiment because we're not sure if the experimental outcome was done by which parameter. So we did not conduct the experiment, but we can predict what would happen.
The length of the magnet split changing its influence.
The length of the magnet? Well, again, if we change the length of the magnet, then because if we change the length of the magnet, you would also change. That means that you would also add multiple magnets to the magnets. So you would change two parameters again at the same time. So we don't conduct the experiments.
Would you like to explain the boundary condition about the?
Oh, yes, sure. Can I get your page where the... So, does the opponent mean in, sorry. This boundary condition? This, okay. So, we after experiments, we found a boundary condition for the angular velocity. And we found out that after 65 radians, which means this is capital omega, and radians is like how fast the angular velocity, how fast the ferromagnetic rod spins. So if it spins faster than 65 radians, then we found out that it fits our theory line. The experiments fit our theory line, and this is 70, I think 75. This is I think around 80, and this is 85. These four experiment data, we confirmed that it would have like a successful climbing rate. However, when it's below 65 radians, we found out that it's unstable climbing, or even there are some situations when it's just not even climbing at all. And this is because like the static friction to the horizontal component is not strong enough for the magnets to spin, so it will not climb or have a unsteady climbing.
So it's above the 65, it won't start the magnet to spin.
No. If it's higher than 65 radians, then we have a successful climbing. It will be like really smooth. Like there won't be any delays. It won't go back down. It won't spin at the same area. It will just go upwards very smoothly. But before 65 radians, there could be some situations where, like I just mentioned, it could like spin at the same place, or it will even maybe it will go down. Yeah.
So after the 65, then for your addition to zero.
Yes. It would have we assumed a theory line, and the experimental data fits our experiment. When the angular velocity is higher, then the climbing rate of the magnet will also be higher.
How do you control the magnet to to stabilize come to the rod.
Okay, so first the problem statement asks us to use neodymium magnets, and neodymium magnets are a really strong type of magnet. So we wouldn't really have to stabilize the connection between these two, the rod and the magnet, because it's already very strong. It would be stuck on its own. And if you're asking about the stabilization of the magnets, we only used a ruler to limit the magnet's motion to the vertical direction, because as we mentioned, it will need to have the stick-slip phenomenon in order for the magnets to climb upward. So if we stabilize the ruler, stabilize the magnet completely, then it will not go up at all.
Okay. Well, the sound of the voice influenced by the velocity of the spin.
Repeat your question.
Sound
The sound?
magnet.
Do you mean the sound will? What do you mean the sound will happen?
When the velocity is up, maybe the sound will go higher.
Well, we actually, in our conducting experiments, we actually did hear some sounds, but we didn't really find it to be significantly higher. Maybe it's because human ears sensing or something, but we didn't find it to be significantly higher.
So you think there's not a very strong relation?
Yeah, we would consider it to have a strong relation. Yes.
You show me the formula page.
Yes. Do you want the force analysis? This.
Why the low part is a bigger force?
Well, because as we mentioned, the torque equilibrium will be equivalent to the static friction divided by static friction times half of the magnet's length, and it will be equivalent to the normal force times omega. So through this equation, we can see that the normal force is actually at the lower part of the contact point, and also because in order to make our climbing explanation work, the normal force in the lower part is relatively higher, and this is because it would have to receive a bigger normal force, so the contraction between these two would be positive, and it would actually cause the magnets to pivot around that point. So if it doesn't have a bigger normal force, then the climbing will not happen at all. And having the lower contact point having a bigger normal force also proves our assumptions.
So each time you refer this experiment, that point is the same.
It's at the same angle. However, the instantaneous center of rolling is changing continuously, because, as we mentioned, these four happen continuously for the magnets to repeat to climb up. So when it's back at this point, then the contact points align at the center. Then it would again slip to the side, and then it will have change the ICOR.
So in each situation, the point will change the displacement.
It's at the same angle, but it will change. Instantaneously.
Okay, time is up. 有空人还是 a minute to summarize.
Okay, from the discussion with the reporter, know that a record they have a meter due to some teachers that didn't do such as about the length of magnet and also the material of the rod, kind of that parameter. But then explain this experiment so well, and explain how the carbon magnet climb. And I got the main point of it is the state and the state of the magnet to the rod. And also explain the.
Time is up. Okay, the reviewer is set to go. You have 3 minutes.
So first of all, I would like to ask both the footer and the opponent. So what is the dominant parameters that affect the climbing rates?
The dominant parameters?
Yes.
Well, we wouldn't change 2 parameters at the same time.
Yeah, I mean the rate of how they change.
Well, it would have to depend on how the slope of the fitting line changes. So if the slope of the fitting line is higher, then theoretically it would then it would be higher. Then it would be more dominant.
And
You mean the main factor of the
Yes, yes.
velocity? I think that is about the magnet mass.
okay, good. So questions to the reporter at page 20. Please. So your variable is the mass, right?
Yes.
So how do you control different mass?
So it's actually, we conducted the experiment by adding lead sheets. So lead sheet is like lead is a metal, and the sheet of it is like a very thin slice, of metal. So we wrap it around the magnet to ensure that it adds the mass but doesn't change the magnet's strength, and also it won't contact the ruler.
Okay. So from the discussion part, the opponent asked how does the contact area affect the results. So I would like to ask how will it affect if the length from the rod and the ruler was controlled?
The length and could you rephrase your question?
Yeah, I mean in your discussion you refer with bigger contact area. That means that the distance between the ruler and the rod is shorter, right?
No. We said that the distance that it could have the stick slip phenomenon would be shorter.
Okay. So what about the opponent?
On the discussion with the reporter, it might be the only difference of it is the velocity of magnet will slow down.
Okay. So last question for the reporter. So what do you think about the magnetic force that affects? Like what does the magnetic force change? What does it affect?
If we change the magnetic force,
Yes.
if we make the magnetic force larger, like we mentioned in the discussion, theoretically it would cause the magnets to climb slower.
Yeah. Okay. That's for my question.
We have 2 minutes preparation time for the reviewer. reviewer has 4 minutes to present his viewpoints.
Okay, so this is the reviewer from Team Mei, and today I'll be reviewing the problem number 4, climbing magnets. So this is the problem statement, and the main focus for the main focus of the opponent, the reporter, is that the reason why the magnets climb up and how relevant parameters affect the climbing rate. So here's a review of the report. So they observed the phenomena is that the magnets move vertically up and spin while it climbs up. And they use stick slip to explain the phenomena. And also pure rolling makes the magnets to go up. And in the experiment, they changed the angular velocity of the rod. And also they find the ICOR in their theory part. And also they changed the map to see if there's any difference in the climbing speed. And the conclusion would be that the stick slip phenomena happens multiple times. So the magnet is able to climb up continuously. And also the mass of the magnet is negatively correlated with the climbing velocity. And we think that the reporter makes very clear theory explanation on the phenomena. But our suggestion is that he can spend more time on the discussion with the experiment data and also compare the theoretical data with their experimental data. So, and here's the review of the opponent. So we think that the opponent has a very sharp and well-structured criticism. And also they use alternative approaches. But our suggestions would be that they have some missed key flaws and their communication could be better. So here's the opponent's question to the reporter. So the opponent asks, how does the material affect the phenomena? And the reporter asks that the ferromagnetic rod satisfies the problem statement, so there's no need to change the material of the rod. And the reviewer thinks that the change of the material would also affect the results. And the key discussion from the opponent, they ask, how does the contact area affect the climbing motion? And the reporter says that when the contact area is bigger, the stick area is shorter. And the reviewer agrees with the reporter. So the opponent asks, how does the change in magnets length affect the experiment data? So, and the reporter asks that by changing the length, multiple parameters could be changed at the same time. So, and the reviewer asks, what is the dominant factor affecting the climbing rate? And the reporter says it depends on, since they don't change two parameters at the same time, so it depends. And the opponent answers that it's the magnet's mass. So here's a key point missed. And in the theory part, we think that the magnetic moment generated due to, since the ferromagnetic becomes temporary magnets due to the magnets attached. So there might be some magnetic moment that leading to the torque on the climbing magnet. And also, they didn't do the parameters using the different materials of the rod. And that's all my review. Thank you.
Summary time for the reporter, 2 minutes.
Now we would like to give our concluding remarks for this problem. So first, we agree with the reporter and the opponent and the reviewer that if we change the contact area to be bigger, the whole magnet's motion will climb up to be slower. It will have a slower climbing rate, have a slower velocity. And the reason that we did not conduct the experiment that add multiple magnets, it was because it would change two parameters at the same time, including the magnetic strength and the mass. So we did not choose to conduct this experiment. And we'd like to also clarify, for angular velocity, the boundary is when the rod is spinning below 65 radians. And the static friction At this stance, the static friction is not strong enough to make the magnets to spin. And but if it's over 65 radians, then the climbing speed will match the theory line. It will go up as the angular velocity will as when you increase the angular velocity, you will also the climbing rate will also go up. And for number 4, if we stabilize the magnets completely, the magnet will not be climbing at all. It would need some space for a sixth phenomenon, just like we included in our no climbing verification. And the lower contact area will have a greater normal force compared to the upper contact area. And this allows the magnets to spin and climb upwards eventually. So having the larger normal force at the bottom of the contact points compared to the upper contact point is a major condition in which have to occur for the magnets to climb up. And last and finally, the reporter would like to clarify that there are 2 major reasons for why the magnets climb up. First is the sixth phenomenon, and the second one is because of the pure rolling. And the pivot of the pure rolling is called the instantaneous center of rotation, which is the IC/OR. And that is the end of our concluding remarks. Thank you.
Okay, thank you. Questions from jurors? Any questions? Okay, I have a question. So the reporters say that the friction is the main factor to make the magnet climb up, right?
Yes.
So what's the reason of the friction?
Well, we look at the page
Sure.
analysis, then sorry. Here. So friction is to this direction, to the horizontal direction, and to the upper, to the perpendicular direction. It's because there's no wait. Because there no, to the vertical direction and the perpendicular direction, because there is no horizontal direction of friction, and it is static friction.
Okay, that's right. So my question is, you are talking about the strength of the magnet, right? The magnetic field strength between the magnet and your rod, right?
Yeah.
And the stronger magnetic field, you say that will slow your climbing speed.
Actually, we used our force analysis to have this assumption and this guess. We're not sure, but that was our prediction.
Yeah, I know. So I want you to think deeply about this issue. Because you have to think about the normal force, where the normal force comes from. That depends on your magnetic field strength, right?
Yes.
So if you have stronger normal force, that will make your friction stronger or weaker.
It will make your friction stronger. Yes, stronger.
So does that conflict with your opinion previously?
Maybe it wouldn't be as strong as maybe it would be as strong to make the friction to be large enough to go against the normal force of the magnet. However, we're not entirely sure. We're only making predictions, so we are very open to any corrections, because the reporter thinks that he could definitely be wrong about this part.
Yeah, I just want to mention that this probably an interest point you have to
Consider.
Yeah.
Thank you.
Okay. And how about you thinking about this problem?
So as the magnetic field strength increased, so for my opinion, the force that makes the magnets climb is not only the friction, but also since when we attach magnets to a ferromagnetic rod, the ferromagnetic rod will kind of become like a temporary magnets. And so so the condition of the magnetic field will be pretty complex. And as the reporter says that the phenomenon is that when the stage 3 happens, So the magnetic it slips. So the center is not on the original spot, and that might cause that how the magnetic moments it will apply the torque on the magnet, so that it affects the climbing situation.
I think when the strength of the magnet is more strength, then it will climb more faster, because when the climbing magnet, how the climbing magnet climbing is that when the magnet and the rod spring and the part of the magnet will not contract with the rod, and in the end the strength of magnet will stick the magnet back to the rod. So while the strength of the magnet is more higher, I think that will stick the rod more highly in every time.
Okay, thank you.
I have one open question. We know the road will climb up, right, according to your condition.
Yes.
So what kind of condition we can hope for this velocity is zero, climb up is zero? Means just make a steady rotation, no climbing up and no climbing down. Is possible? For three guys. For all for your condition, right? But you can add something or speed down.
Okay, so in the reporter's experience, they add a ruler to block the horizontal direction motion of the magnet, and so if we want make the magnet spin and without climbing, so maybe first of all we need to so the ferromagnetic rod in the middle, if it spins still, like can I use the blackboard to explain?
Yeah, sure.
So the ferromagnetic rod, if acts in the condition of the reporter, so this rod in the middle is stays still, so it only spins. But if we want the magnet to stay still, first of all we need to remove the ruler that block the magnet, and secondly we need to make sure that the rod in the middle it only spins. So for some situations the rod might have a condition of this. So if the rod in the middle, the motion of it was not limited only on spinning, it might causes the magnets to rise even without the ruler blocks. So if we want to create a stable spinning condition, we remove the blocker, and also we make sure that the rod in the middle stays still.
So, like we previously mentioned in our report, we had a verification for for the angular velocity. So this is when unsuccessful climbing can be defined as when the capital omega is lower than 46 by radius, then there could be a possibility when the velocity is zero, which is not climbing at all. And in this case, it means that the magnet is spinning around at the rod without any perpendicular direction. So if we want the situation for what the jury predicts, then yeah, we have to first remove the ruler to let the magnets rotate around without only blocking the vertical direction. Then I think there could be a possibility in which when the capital omega is small enough, it could happen. It could happen that the magnet's only spinning and not climbing.
So you mean slow down the omega, right?
Yes.
Okay.
And previously we talked about the explanation of the velocity. When the velocity is low enough, the magnet will keep circle in every time. And maybe we can change the shape of the magnet if the magnet is totally fit on the rod. And that's my can let the magnet circle the rod every time.
So to change the shape.
I think that is the way.
Okay. Okay, thank you.
Questions? Okay. Right, so, thank you. Okay, the scores for the reporter. Eight, 9, 7, and 9. Scores for the opponent. 4, 4, 4, 4, and 6. And the scores for the reviewer. 7, 7, 8, 6, and 7. Okay, this concludes our afternoon session. Thank you very much for taking part in this session.